Physics 20B. My name's James Bullock. I'm the professor. This course is on the subject of cosmology. And to tell you a little bit about what that course is, what it's about. I'm not sure if it's easy to see. Let me see if I turn off one more light. I wanted to start with this picture before I go into what we're going to be doing in this course. So this is a picture that was taken by a guy named Art Roche, who was out somewhere in the southwest taking images of the night sky. I thought this was a particularly beautiful picture, so let me, well, I won't turn all the lights off since people are coming in. If you can see, maybe you can't see, the room's a little bit bright, but along the walls here, this is some canyon. So he's inside a canyon, and he's looking up at the sky. And he's taking a deep image so you can see these clouds and stars and things in the sky. And he told me that if you look along the walls of these caverns, there are all these ancient petroglyphs that are carved into the walls. And so these were carved into the walls by ancient people living in North America, 1,000 years ago. And the reason why I really like that is because the sky basically looked identical to them, more or less, than it does to us. And you can also imagine that when they looked up at the night sky, they were thinking a lot of the same questions that we think, or that we ask ourselves when we look up at the night sky. Okay, so when you look up at the sky at night, and you're way away from the city, and you just have time to ponder things, you might ask yourself things like, well, how many stars are there? And how long have they been there? And what are we in relation to all these other things that I see up there? How old is the universe? Yeah.
Can we turn the lights off for just a second? So
yeah, let's turn them off. People are done. So that's a little better. Yeah. So you can see there's the cavern, there's all these carvings in the wall, and you can look up and you can see all this stuff. So, like I was saying, you can imagine these people are asking themselves things like, how old is the universe? How did I get here? Has it always been this way? What are these bright things in the sky that are shining? And those questions are exactly the same questions that we try to answer in modern scientific cosmology. Okay? Except we're trying to answer them using empiricism. Okay? So the idea is you try to ask questions, get an answer, see if that's consistent with all the available data, and begin to build a picture of what the universe is really like, basically by repeated experiment, or repeated observation. But at the end of the day, we're trying to ask the same questions that people have always asked themselves when they look up at the sky. And that's what this course is about. So some of the big questions that we'll talk about in this course are, how old is the universe? How did we get here? How far away are the stars? How big is the universe? And then other things that these ancient people weren't thinking about, like what are black holes? What was the Big Bang? But of course, this idea that there was a Big Bang is fundamentally linked to this question of how old is the universe, or how did we get here? So all of these things are interconnected and they're really driven by the same sets of questions. So that's what we're going to be doing in this course. The other big questions in the course are, how are you going to assign the grades? That's what this is. Okay. So basically, this course is going to have two tests, two midterms. One midterm basically in the middle of the course, and one midterm at the end of the course. And they're each going to cover about half the course. Okay. The dates of those are Friday, February 11th. This is going to happen in discussion section. And then on the last day of class, we'll have the second midterm. Now, this particular discussion section is the most important one. And I know there are some of you who are trying to get in there are some discussion sections you can't make, and some of them are full and some of them are not. I don't know exactly what the current status of that is. The one that's going to be the most crowded is this Friday, February 11th, because that's the one everybody has to be at to take your test. And you have to be in your assigned discussion section on that day. Now, these midterms are basically going to be tests on retention. Okay, did you come to lecture? Are you paying attention to what I'm saying? Are you reading along the textbook? Have you done basic? Have you done the homework? That kind of thing. So that's basically the goal. Now, the second type of assignments we're going to have in this course are basically projects. So I'm just going to call them generally projects. So it's basically homework assignments. And one final class project, which is going to be due towards the end of the quarter on March 4th, that I'll talk more about as the course progresses. But these will help you explore things a little bit more deeply than what we're going to be covering on the tests. And specifically for the class project, it's a very open-ended kind of thing. Basically, I'm going to ask you to pick one thing. One idea, one concept, one historical figure, something like that you think is interesting in the whole field of cosmology, okay, and explore that in more depth. And so this is meant to sort of give you the opportunity to get excited about something and then spend time on that. So I'm very open to lots of different ideas for this final project. The most important thing for me is that you get excited about it and work hard on it and get something out of it. So we'll talk more about that later. One of the ideas for the final project is I want to allow you guys to play to your strengths and your interests. So if you're more of a poet, okay, you can explore things like, you can even do visualization stuff, like do an art-related project. I can talk to you more about these ideas later. You can do something more creative, like last year I had a particular project that was this really creative movie that was turned in, that was basically like this whole skit about the origin of modern cosmology and the ancient Greeks and how they came about building their picture of the universe. So it's, you know, it's sort of an opportunity for you to do something creative, interesting, that you want to sink some time in and actually do something that you find fun. Now, another possibility is that you can do something more like a mathematical kind of calculation. So if you like math, you can do something more quantitative. I've had people build computer simulations of galaxies colliding and stuff like that. Lots of different things you can go in that direction. But anyway, I just wanted to introduce this idea now. You can actually download, I think I put a final project description on the course website already, so you can take a look at it and start thinking about it. This is a big chunk of your grade, and I'm basically allocating a significant amount of time for you guys to work on it. So, you know, before I go on to start talking a bit more about this course, you know, in the end of the day, what you get out of a course is related to what you put into it. And so I'm here to sort of kindle your interest and try to talk to you about the things that I think are most interesting about it. But it's really hard to actually get anything out of a course without spending your own time on it. And so that's really what this slide is supposed to be about. The time you spend away from class, thinking about the subject, working on your homework, working on your final project, or whatever, is the most important time. And it's that stuff that you will take with you. It's very hard to sit passively and listen to someone blab on and actually get something out of that. And so that's really what this slide is about. One of the things that I hope we get out of this course, maybe even during lecture, but then beyond lecture, is it'll encourage you to maybe think about things that you haven't thought about before. And don't necessarily take everything I say for granted either. Okay? if even during lecture, if I say something and you think it's wrong or you don't understand why I would say such a thing, make sure you say something to me back. So I really hope that this course is interactive. I encourage everybody to speak up, but think on your own. Go off and think about stuff on your own, and then come back and you can have more questions and we could bring them up. The thing that I'm okay with you, for example, if I give you a homework assignment and you want to read your book, and obviously you're going to read your book and try to answer the questions, but you're also free to sort of explore any other resources that you can find in the library, even on the web, although you need to be careful with certain websites. That's okay with me, but as long as you avoid plagiarism. That is, if you find something that's like, say you want to write a paragraph on Aristotle, do not just take something transcribed from the web on Aristotle. That's really bad, and if I catch you doing that, I'll fail you. Now, if you want to say, I got this information from this website, blah, 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 as long as you cite sources, that's fine. But especially in the final project, do not plagiarize anything. Okay. So I wanted to sort of get out of the way the logistical stuff for the course, and I've kind of laid that out now. Does anyone have any questions just about that? Sort of logistics of the course and how things are going to go? Yeah?
So do we not have an exam during the exam?
You do not have an exam during the exam week. So the idea is that the final project is your final, so there won't be a final exam during the exam week. Anything else? Yeah. There's no discussion this Friday. Thanks for asking. I sent an email out, but probably people haven't gotten it yet because I just sent it out recently. So discussion sections are canceled this Friday. They will happen next Friday. I'm going to hand out your first homework coincide with next lecture. Oh, that reminds me, actually. A lot of this course is going to be done via the website, and I think a lot of courses do that now. I've been here long enough that when I first started teaching, that was unusual, but now I think everybody does it. All of your homework is basically going to be handed out on the web. So if you go to the class website, there's a link to the schedule. On the schedule, it'll say the lecture one was on whatever. You can download the lecture. It'll be a PDF file of the lecture. And then on homework days, I'll make available a PDF of the homework. You can just download the PDF. And I'm asking you to turn the homework in to the TA's mailbox on a certain day by a certain time. And all that information, again, is given on the website. The syllabus is also up on the website. So all of the things that I've kind of gone over here about how grading will be done and all that kind of stuff, that's laid out in great detail on the syllabus, which is you can get the PDF on the website. Anything else? Let me just add one more thing now that I'm thinking about it. I cannot sign, add, or drop cards. Physics faculty cannot do that. So if you want to add or drop the course or do any of that kind of stuff, you just have to go to the physics main office and they deal with that. They don't give me the power to make those kind of decisions anymore. Yeah?
Were all the discussion sections mandatory?
No. So discussion sections are not mandatory. Basically, most of the discussion sections are just there for you as sort of helpful tools. You can go and ask questions about the homework. The TA will go over problems, etc., etc. We'll get you ready for tests, and that kind of thing. But you don't have to go. You don't want to. I would encourage you to go. The only one that's mandatory is the one where we're giving the first mission. Yeah, so my philosophy on this is that you guys are adults. I'm going to give you all the information you need in this course, and you can do with it what you will. So I don't like taking attendance, and I don't like all that kind of stuff. You guys aren't kindergartners. Do what you want to do. Anything else? Oh, one other thing. I keep doing this. I'm going to experiment with doing a podcast on the lecture too. I've never done this before. Has anyone had a class where they've done this? Is that a yes? Okay. Any feedback on whether it works or not would be useful. I'm trying out the software now, and I'm going to see how it works, but I might be able to post podcasts of the lectures, including my voice and the slides. So we'll see how that goes. Okay. So anything else? Okay. All right, so this is the first lecture. And I'm going to start talking about what is cosmology. And then a couple of different basic ideas in cosmology before we get into the meat of the course. So again, this is all basically introductory material. Now, this is an overview of what modern cosmology is. This is sort of the story that we put together based on the last, 600 years or so of evidence. So, the standard picture of cosmology right now is that space and time, all space and time itself, began about 14 billion years ago in an event that's called the Big Bang. And the universe has been expanding and cooling since then. Okay, so what I mean by that is, even though empty space right now is very, very cold, back in the past, when the universe was smaller, it was much hotter. The universe was very hot at early times. In fact, it was so hot at early times that normal stuff couldn't exist. Okay, so imagine you're in this room and everyone left the room, because we don't want to get gruesome here, and I started turning the temperature up. Eventually it would get so hot that the seats would melt. Okay? And everything would be liquid. And if I keep cranking up the temperature, eventually the liquid would boil, and you would have nothing but gases. And then if you see, even at that state, the whole room is much simpler than it was before. Because when things are that hot, it's hard to have complicated things like chairs and even people. Everything's just a gas. So all the atoms are basically separated from molecules. Let's say at some point, so now all the molecules aren't bound together, they're all moving around very quickly. At some point, if you keep cranking up the temperature, it's so hot that even molecules can't hang together. So they ram into each other and break apart. And then it gets very simple, because all you have is just a sea of atoms. There's nothing complicated. It's so hot that it's just a sea of atoms. Then you keep cranking the temperature up. It gets even hotter, that gets so hot that atoms now come at each other and they run into each other going so quickly that they break apart. That the electrons can no longer stay bound to the nuclei of the atoms, and basically that's called a plasma. All you have is like nuclei of atoms and free electrons, and then that's what you have. If you keep cranking up the temperature, eventually it gets so hot that even the nuclei of atoms can't hang together, and all you're left with is a sea of neutrons and protons and electrons. And you can see at that state, everything in this room is extremely simple. It's nothing but neutrons and protons and electrons, moving around very quickly. And that's an analogy for what we think was going on at the very early universe. It was so hot that nothing complex could exist. And it really was something more like a primordial soup with fundamental ingredients. The basic building blocks of all matter existed at that early time. And then as the universe cooled, more complex things can happen. So eventually, as the universe cools, stuff can start to get made, like galaxies. Okay? So galaxies eventually form, and within those galaxies are stars. Galaxies are made up of stars. And around those stars, planets form. Okay? And about 4.5 billion years ago, about a third of the way back to the Big Bang, our sun formed, and the Earth formed at about the same time. And so over the last 4.5 billion years, our Earth has evolved. And this is where we are. So the picture is that early on, the universe was quite simple. Very, very simple, it turns out. And as it cooled, more complex things could happen. And eventually, you get planets and stuff like that. And even on these planets, you have life. And life is extremely complex. Now, I've just told you a pretty fantastical story. Okay? This is a pretty crazy story. about how the universe is expanding, all space and time began at one point, it's 14 billion years old, etc., etc. And the thing I want you to think about is, how the hell do I know that? Why should you believe me? Yeah?
Satellites looking into the past, like the Hubble Space Telescope looking into the past.
Yeah, so that's right. So there are things like the Hubble Space Telescope that can look at galaxies that are far away. Since they're far away, it takes time for light to get to us. I'll talk about this idea later. We can use them to sort of make a consistency check to see whether these stories are correct or not. But it's not just like one thing that looks and sees something and like, oh, that's consistent with the picture. All of this story, this seemingly very fantastical story that I've just told you, is built up of tiny, tiny little pieces of information and data and people striving to prove each other's theories wrong, etc., etc. So that the term the Big Bang, a lot of people don't know this, is a term that was initially coined to be derisive of the idea. Okay? People had this idea that maybe the universe began in this kind of hot fireball. And there were other physicists working at about the same time who did not like this idea, who thought this idea was crazy. Okay? And started derisively calling this theory the Big Bang. Oh, the Big Bang, yeah, that's how the universe began. Okay. But eventually it was such a catchy name that even the people who liked the theory started calling it the Big Bang. It sort of backfired. But the reason why I sort of say that is so that you'll keep in mind that it's not like a bunch of people jumping on a bandwagon for the sake of it. Okay? If I could prove that this model was wrong, I would have a Nobel Prize and my life would be great. Okay? I can't. I've tried, I can't. Okay? Now, I'm not the smartest person in the world, but there are lots of smart people who are trying really hard to kill these theories, because if they do, they get famous. Okay? If I could prove Einstein wrong, it would be good for me. Okay? So it's not like a bunch of people who are like, it's not like we're trying to, it's not like there's some, there's not like there's a curtain and we're all the Wizard of Oz trying to convince you that all this stuff is true and really we have no evidence for it. There's a tremendous amount of evidence for this stuff. And one of the things I hope to do, at least in bits and pieces in this course, is to talk to you about why we believe these things. And how these, how this seemingly fantastical story was built up. And one of the things that's quite amazing about modern cosmology is, in almost every step of the way, we've been forced to accept ideas that were seemingly crazy and impossible to imagine from the previous generation. This goes back to something as simple as we're actually going around the sun and the sun isn't going around us. That was a seemingly crazy thing to a lot of people. But eventually there was so much data that rational people had to accept that this is the truth. And since that time, progression has been that way. So I wanted to mention to you a sense of time. So I talked about this 14 billion year number. Okay. So the universe is 14 billion years old. And that's 14 followed by 9 zeros. Okay. So in this course, we're going to make sure we know how to use scientific notation. All right, and if you remember, the way you write this number in scientific notation, it's 1.4 times 10 to the 10, where 10 is the number of decimal places that you move the decimal point over. Okay. I hope everyone's seen scientific notation before. Who has not seen scientific notation before? It's okay if you haven't. Good, all right. Now, if you're not comfortable with it, you should get comfortable with it. Okay. And that's the kind of thing that the TA will go over in class. Okay. But 14 billion, a neat way to write it is 1.4 times 10 to the 10. You see, it's a lot faster to write this. And I don't have to count zeros all the time. If I had to write numbers like this, it would just be awful. I'd screw up all the time. But this way you can see, all right, so 10 to the 10, I know how big it is. It's 1 times 10 to the 10. Okay. So if you take this amount of time, just to give you a comparison, and you scrunched it all down into a single year, okay? then all of recorded human history would have occurred in the last 13 seconds on a relative time scale, compared to a year. Okay. And Shakespeare was living and writing his plays about 1 second ago out of this year. So, a very old universe. So this is how you write the number again in scientific notation. I'm just going to put this up on the web so you have other examples of how to write scientific notation. Okay. Now, when you're dealing with numbers that are this big, okay, like in cosmology, we're going to be talking about distances that are really large, times that are really large, etc., etc. It becomes very useful to write things in terms of scientific notation. Okay. So here's another example of writing something in scientific notation. It turns out that 1 year is equal to this many seconds. About 31 million seconds. Okay? So that's about 3.1 times 10 to the 7 seconds. So that's another way of writing it. So if I wanted to know how many seconds there are in a year, it's 3.1 times 10 to the 7 seconds. If I wanted to know how old the universe is, it's 1.4 times 10 to the 10 years. Now, how is it that I was able to say that Shakespeare was living and writing his plays 1 second ago, if you take the full expanse of time and stretch it down into a year? How was I able to figure that out? Well, the way you do it is with ratios. Okay. So let me show you how you do it with ratios. So the universe is 1.4 times 10 to the 10 years old. Okay. Now Shakespeare lived in 1568, and that was about 440 years ago. Okay. So what I could ask is, what's the relative size of 442 years ago compared to 1.4 times 10 to the 10 years? Because that's the fraction of the way back to the Big Bang that Shakespeare was. Okay, he was 440 years ago. I can compare that to 1.4 billion years ago. What fraction of the way back to the Big Bang was that? Okay. And then I want to say 442 years is the 1.4 times 10 to the 10 years as what is to 1 year? I want to figure out, okay, that same fraction relative to a year is how many seconds? So the way you set up this problem is you say the ratio of 442 years to 14 billion years is this. Okay, and I want to say that's the same as some little amount of time is to 1 year. People know what I'm doing here with this setup? So now what I want to do is I want to solve for x. And to solve for x, I just multiply both sides by 1 year and I get this. I get x is equal to 4.42 times 10 to the 2, that's 442 years, divided by 1.4 times 10 to the 10 years. And this is a pretty easy fraction to do now because I can see this roughly is going to be something like 10 to the minus 8. Just in the exponent, I got 10 to the 2. I divide by 10 to the 10, so then that's the same as having 10 to the 2 minus 10 in the exponent. And what you end up getting is something like 3 to the minus 8 years. Okay? So compared to a year, Shakespeare was living just something like 3 times 10 to the minus 8 years ago. Now, if I were to say to you, if you took the full expanse of time and stretched it down into 1 year, Shakespeare lived 3.16 times 10 to the minus 8 years ago, you would say, what? Okay, so I wanted to convert that into seconds. So I want to change years into seconds. Remember, I already told you that a year is 3.16 times 10 to the 7 seconds. So I can stick this, I can replace this year times 3 times 10 to the 7 seconds, and when I multiply those numbers together, I get 1. So on this ratio, I get 1 second when I compare it to a year. Does that make sense? Hopefully. Okay, yeah.
Is this squiggly equal sign?
Squiggly equal sign is like approximate. It's not exactly right, but it's close. So the conclusion is that 442 years to 14 billion years is the same as 1 second is to a year. So this kind of ratio problem is the sort of level of mathematics that I'm going to expect you to be able to do in your homework and on tests. It's not going to be just that, or your grade isn't going to be totally based on problems like this. But because this course fills a basic science requirement, I'm required to do a little bit of mathematics like this. This is the kind of thing that you should be able to do. Now, some of you who are engineering majors or physics majors, this is not going to be a problem for you. I know that. Okay. But some of you who haven't done mathematics since you were in high school, maybe you're really good at it, and then you test out of all your requirements, and then you become an English major, and you haven't done it in a long time. Okay. This is going to be a little bit more challenging. That's okay. All right. Understand that some people spend all their time doing math, and so this kind of stuff is going to be easy. Other people spend all their time reading and writing essays, so this kind of stuff is going to be harder. But it's going to even out in the end. Okay? All right. Are we good? Questions about this? So if you do have questions about this kind of stuff and it freaks you out, come talk to me or talk to your TA, and you will be able to do it. Now, another thing that's actually very important in the context of astronomy and cosmology is the fact that light doesn't travel infinitely fast. It travels very fast, but it doesn't travel infinitely fast. Okay? So what I mean by that is, although your perception is that you turn the light switch and the lights come on, and it's instantaneous, it's not exactly instantaneous. It takes some time for that light to get from the light bulb to your eye. And the speed with which it travels from the light bulb to your eye is about 300,000 kilometers per second. Okay? And that's the same as 3 times 10 to the 5 kilometers per second. And that's also the same as 186,000 miles per second. Okay? Now this is really fast. Okay? And you would never notice this on Earth. Light can travel around the Earth 10 times in a second. So the speed with which it's traveling is sort of mesmerizing. But if you think about the sun, which is very far away, it's much farther away than 10 times around the Earth. It starts to matter that this is not infinitely fast. In fact, it takes 8 minutes from light to get from the sun to the Earth, approximately. So what that means, if you think about it, if you look at the sun, you're seeing the sun as it was 8 minutes ago. It's a similar effect that, if someone's across the canyon from you, and you're in a big canyon, and someone yells, okay, it takes a little bit of time for that sound to get to your ear from when the person yells. And that's what happens with an echo. So if I yell out into a canyon, I say something, and then I hear it. And that's because it's gone and bounced off a far wall and come back, and that's taken a little time. So there's a delay, there's a little lag time in how long it takes sound to travel. Light's doing the same thing, and that kind of lag time starts to matter when the distances get big. Now it gets a little bit more interesting when you think about the brightest star. So the brightest star in the sky is so far away that it takes light about 8 years to get to us from it. So when we look at the stars in the sky, we're seeing them as they were years ago. Not as they are now, but as they were years ago. Now, the thing about it is that the distances to the stars are really small compared to the size of the Milky Way galaxy itself. One of the things we'll learn about in this course is eventually humans were able to figure out that the galaxy is huge. Okay? There are about 100 billion stars crammed within our galaxy. Okay? And it takes light 100,000 years to cross our galaxy. So traveling at 186,000 miles per second, it takes 100,000 years for light to go from one side of the galaxy to the next. And it takes 2.5 million years for light to reach us from the brightest galaxy, Andromeda, the nearest bright galaxy, Andromeda. So that is, okay, the galaxy is this big. It's 100,000 light years across. We have a neighbor galaxy called Andromeda that's not very far from us in the scheme of things. It's like over here. It takes light about 2.5 million years to get to us from that nearby galaxy, Andromeda. Okay. So this picture here of Andromeda, this is a picture of Andromeda. This is what it looked like 2.5 million years ago. It's not what it looks like now. So this is in fact what Andromeda looked like before there were people to look up at the sky. So when people talk about looking back in time with astronomy, this is the kind of thing they're talking about. When we look at distant objects, we're seeing them as they were, not as they are. Another way to think about this is, imagine that you're in ancient times and you have some messenger who's carrying you news of a battle. Let's say you're a king. Your kingdom's in a great battle that's 100 miles away. And if you win this battle, you're king for life. And if you lose this battle, you got nothing. Okay, you're not king. You're going to get destroyed pretty soon. The battle happens. So you have no idea what's going on. You don't know whether you're king for life or you're going to get executed. But there's a messenger coming on a horse carrying the news of the battle. And when that gets to you, that's when you finally find out what happened. So it's kind of like that. There's an ultimate speed limit for how fast these messengers can travel, and that's the speed of light. Are there any questions about that? So, the interesting thing about this is, what this allows us to do is as we see things that are farther and farther away, we're seeing the universe as it was longer and longer ago. So when we look at Andromeda, we're seeing the universe as it was 2.5 million years ago. But the most distant objects that you can see with the Hubble Space Telescope are so far away that it takes light 12 billion or even longer, 12 billion years or even more to get to us. So in fact, this galaxy right here was imaged by the Hubble Space Telescope. It is so far away that it took like 12 billion years to get to us from this object. So this is a picture of a galaxy that existed before the Earth existed. And one of the interesting things about this galaxy is you'll see that it looks different than this one, which is nearby, which is representative of the local universe. It was more messed up. And what you see is that as you look at galaxies that are farther away, which means as you look back in time, galaxies tend to be more messed up looking, like they're not done forming, compared with ones that are local here. You got a question?
I have a question. Like from the sun to here, we can see that it's like 8 minutes. But how do we know something that's like 12 billion years?
So that's a great question. So there are a series of methods that we'll talk about in this course for how astronomers measure distances to objects. Okay, so you could have started that question with, how do we know that the nearest stars are 8 light minutes away? How do we know that how far away they are? And how do we know how far Andromeda is? And how far do we know all these other objects? So all I can tell you right now is that there are precise methods that have been developed to measure these distances. And that's one of the topics of the course. And so it relies on a series of kind of bootstrap methods that people have figured out to measure distances to objects. It turns out that one of the ways we can measure a distance to this object is by studying the light that it emits and looking for something called redshift. And redshift is a measurement, is an effect with the wavelength of light that light responds by stretching its wavelength when things are receding from us. And it turns out that we can map that recession velocity to a distance. So it's a complicated series of steps that I'll get to in this course. So that's one of the things I'll talk about. Right. So yeah, and it's very good that you're dubious of me. You're like, you don't know that. Okay? And that's good. I'm glad you have that attitude because you should be very skeptical about this stuff. Okay? One of the things that I think is unfortunate with the way a lot of stuff is taught in school these days is you're basically taught things as facts. And you're never taught why, or you're not encouraged to question. Okay? It's the same way that people living 1,000 years ago were taught that the sun goes around the earth, and everyone's like, okay, the sun goes around the earth. But the question should be is, why, it looks to me like the sun's going around the earth. Why isn't the sun going around the earth? You tell me the earth's going around the sun. Why do you say that? Okay. So that's kind of that's the flavor. I mean, I like that. Okay. Now, another way to measure distance, okay, is by basically taking into account this whole light year stuff. Okay? That is, I said the sun is these stars are so far away that it takes 8 minutes for the light to get, or 8 years for the light to get to us. So one way to characterize the distance is to just say, well, it's 8 light years away. That is, you can turn the time it takes light to travel into a measure of distance itself. And that's what a light year is. Okay? So a light year is 9.5 sub 10 to the 12 kilometers. That's the distance that light can travel in exactly 1 year. Okay, so when I say something is X number of light years away, I'm telling you a distance to that object. And it makes much more sense to talk about the distances to stars in light years, because otherwise I'd have to say things like, well, that star is 5 times 10 to the 12 kilometers away, and that star is 15 times 10 to the 12 kilometers away, and it just gets confusing. So instead I just say, oh, that one's 8 light years away, that one's 12 light years away, etc. So it's just a unit of measure, the same way that a kilometer or a mile is a unit of measure. It's just a really big unit of measure. Okay. But a thing to keep in mind, however, is that a light year is a unit of distance and not a unit of time. So a lot of science fiction movies, you'll see people mess this up all the time. Like, oh, that was light years ago. That doesn't make any sense. Okay, that's like saying that was miles ago. Okay, so a light year is a unit of distance. So based on this terminology, Andromeda, this galaxy I've been talking about, is about 2.5 million light years away, which is the same as 2.5 times 10 to the 6 light years away. Okay. So now that I've introduced this idea of, first of all, time, how old the universe is, how huge the expanse of time is that we're dealing with when we're talking about cosmology, I began to talk a little bit about the huge distances that we're dealing with. There's a popular way to talk about, to sort of try to get your head around distances. That's called powers of 10. So I just wanted to use that now to kind of introduce this concept of distances. And huge distances we're going to be dealing with in this course. So what I'm going to show here, what this is this is zoomed in on a bee. Okay, so just to give away a little bit. Here's a bee. Okay, blown up. And there's a little red rectangle right there. You see it? I'm going to blow that rectangle up. All right? So this is the eye of a bee. So this box is about 1 millimeter across. So 1/1000th of a meter. Okay? And then if I go backwards again, go forward again, and I zoom out by a power of 10, this box is now a centimeter across. And that little box is the one that I had just zoomed in. On. Okay? So that's the difference of a power of 10. It's the eye of a bee to like the whole bee. That's about a power of 10. Now if I go on another power of 10, now I'm 10 centimeters across. And there's the bee, and it's sitting on a flower. Okay? Now I can zoom out by another power of 10. And that flower, that lily pad, is sitting on a pond. Okay? And it's 1 meter across. So now I've zoomed out 3 powers of 10, and I've gone from the tiny eye of a bee up to a pond that's about 1 meter across. So now I'm looking at something about the size of me. So now let's go out another factor of 10. Now we're looking at basically the whole pond, which is about 10 meters across. That's about the size of this room. Okay, we're going to zoom out from there. Now we're 100 meters across, all right, the size of a football field. And this is a park, okay? This is Golden Gate Park, actually. And that little lily pad is right here in the middle. I'm going to turn all the lights off so we can see. So that lily pad sitting right here in the middle. This is 100 meters across. It's a football field for the whole Golden Gate Park. I'm going to zoom out. Or sorry, not the whole Golden Gate Park. A good piece of Golden Gate Park. This is now a fifth of all of Golden Gate Park. It's a kilometer across. Okay? So all that stuff, all that detail that we were talking about was all in here, and we're looking at it from above on a scale of about 1 kilometer. So now I can zoom out from there. This is a big chunk of San Francisco. Okay, another power of 10. We go from a piece of Golden Gate Park to a big chunk of San Francisco. Okay? Another power of 10. This is 10 kilometers. Now 100 kilometers, as viewed from satellite, it's basically the entire Bay Area. And another power of 10. This is seen from about 200 kilometers above, and there are about 7 million people who live within this box. Another power of 10, 1,000 kilometers. This is the state of California, and we're here. Okay? So it's only on this scale that we can think of things as sort of, okay, this is our state, 1,000 kilometers. Now, all of the expansion that I've done up till now, okay, is about a factor of 1 million. And as you'll see, this is not very much, because I'm going to keep expanding. So now if I go out by another factor of 10, there's the Earth. Okay? This is all of North America, 10 to the 7 meters. Another factor of 10. Here's the Earth. 10 to the 8 meters. You can't see the moon. Okay? The moon is farther away. The moon is just outside the picture. The moon's about 4 times 10 to the 8 meters away from the Earth, and this is only 10 to the 8 meters. So the moon is like, over here somewhere. Let's go another power of 10. There's the moon finally. So this is the orbit of the moon. The orbit of the moon is actually pretty round, but this is viewed edge on. So imagine you had a circle that was like that, and you're viewing it sort of tilted. And that's why it looks elongated. Okay, but that's the Earth. There's the pass box. That's how big the moon's orbit is. And this is the track over which the Earth is traveling around the sun. This is 10 to the 9 meters. Okay, 1 billion meters. 10 to the 10 meters. We don't see the other planets yet, but we're seeing a big track of the Earth's motion around the sun. Now, the Earth moves along this path in 4 days. Okay, so in 4 days, the Earth travels more than 10 to the 10 meters. So the Earth is going really, really fast around the sun. It goes about 2.5 million kilometers a day. That's how fast the Earth is moving around the sun. This is one of the reasons why the ancients did not believe it, that the Earth is going around the sun, because it has to go this fast. Now, on another power of 10, 10 to the 11 meters, there's the Earth orbit, there's the orbit of Venus, and there's the orbit of Mars, just barely on the screen. Remember, it was 2 powers of 10 just to see the orbit of the moon. And another power of 10 to really see the Earth. So a factor of 1,000 to get down to the Earth on this scale. Okay, that's the difference between like Golden Gate Park and the Earth. So it's that same scale. It's a huge scale. Let's go another power of 10. Now we can see the sun, finally. There's the sun. The scale is 10 to the 12 meters. Here's the sun, there's the Earth, and we also can just barely see the orbit of Jupiter. Another power of 10. You start to see now, finally, the entire solar system, all the planets going around the sun. You see them on a scale of 10 to the 13 meters. Note that the solar system, remember the Earth is about 10 to the 7 meters or so across. The solar system is about 10 to the 13 meters across. So the solar system is 1,000,000 times bigger than the Earth, than the whole Earth. All right, let's go another power of 10. Basically, note we go out another whole power of 10. We don't see any other stars. There's no other stars out there on this scale. But there is this cloud of rocks and stuff called the Kuiper Belt that's sort of orbiting around the outer part of our solar system. And if you remember this big discussion of whether Pluto is a planet a few years ago, Pluto's no longer considered a planet. Pluto is one of these Kuiper Belt objects, a big one that's orbiting around. And there's a few other that are known out there that are kind of big, orbiting in kind of weird orbits going around the solar system. Okay, that's 10 to the 14 meters. Let's go another power of 10. 10 to the 15 meters. There's really no other stars out there. There's a cloud of kind of very small rocks that are sort of exaggerated in this picture. Basically just dust, crap like that are all floating around in the outer part of the solar system that are left over from the formation of the solar system itself. But there's really nothing big or bright out there within 10 to the 15 meters of the sun. So let's do another power of 10. Still nothing. There's still not another star. And you have to go another whole power of 10. Oh yeah, keep in mind this is where you are. You have to go another whole power of 10 before you start seeing other stars. Okay. So to put this on a scale, if you took the sun, okay, let me talk about how big the sun is for a second. You can take 100 Earths and put them across the face of the sun. So this is the sun. You can line up 100 Earths on the sun. So it's a big thing. If you took the sun and scrunched it down to the size of a basketball, the nearest star would be in Hawaii. So that's how big the distances are between stars, compared to the size of the stars. So now we're beginning to see the nearest stars on a scale of 10 to the 17 meters. So I can go out another factor of 10 and we start seeing lots and lots of stars. Another factor of 10, I still see more stars. I still haven't encompassed the entire galaxy. In fact, I have to jump 2 more powers of 10 before I see all of the galaxy. Okay. So this is about 10 to the 5 light years, 100,000 light years. That's what this scale is. Now, this is not the Milky Way. And how can you be sure that this is not the Milky Way? Yeah. Right. Because we're in it. Okay, we're down here. And you'd have to go 100,000 light years distance to come out and take a picture of it. Okay? So even if we had spaceships with cameras that we could launch at the speed of light, it would take 100,000 years to get to a point where we can take a picture of it. So that's not what's going on here. This is an artist's representation. Okay? A lot of times in the newspaper, you will see pictures of galaxies, and below the caption it will say, the Milky Way galaxy. You know that they've messed that up. Okay. And that's where the sun would be, about here on this picture.
Question?
Yeah.
Why don't we just send like a big mirror in outer space?
So we can look back and see ourselves? I mean, okay, first of all, all right, no, it's an interesting idea. So let me answer that in a couple different ways. So first of all, if we could do that, it would still take 100,000 years to get the mirror there. And then it would take 100,000 years for the signal to hit the mirror and then bounce back to us. Okay? Even if we could send the mirror out at the speed of light. Okay? Because remember, it also takes light 100,000 years to hit the mirror and 100,000 years to come back. Okay? Now, the other problem is, just putting stuff into space is not just. It's very hard to put stuff in space. It's very expensive to put stuff in space. In fact, it would almost cost exactly the same thing to put a pile of bricks that weigh the same thing as the space shuttle into space as it does to launch the space shuttle into space. It basically costs a lot of money to take stuff off the ground and put it into orbit. It's a very expensive thing. And you're basically paying per kilogram of whatever crap you're putting up there. That's the main cost of putting stuff into space. And so when we put stuff into space, it's very expensive. And that's just getting into the low Earth orbit. Then you got to like send it out. You know, it gets harder and harder and harder. The most distant objects that we've ever put out, man-made objects that have gone out in space, are the Voyager spacecraft that were launched in the 70s. And they're now just hitting sort of the edge of where the sun is contributing light. So it's basically beyond the edge of the solar system, but not that far beyond the edge of the solar system. Those are the most distant things we've ever sent. So that's like, 8 powers of 10 smaller than this, or more. So, yeah, it's hard to send stuff out. And what that means, though, is, we've got to somehow figure out the answers to all these questions without ever going there. And this brings me to another point that I wanted to make about this. A lot of people look at these kinds of pictures and images of, wow, look how small the sun is, look how small our solar system is compared to the galaxy and the universe, and it makes them feel insignificant. Does anyone have that kind of, I wonder if people have that. Does anyone feel that way? I wonder. Okay. Yeah. Makes you feel insignificant, maybe. Or maybe it makes you feel like your problems are insignificant, or the world's problems are insignificant, because it's just this little, dot, this little blue dot, somewhere in that big mess of stars where all the action is. So that's one attitude that people have when they study astronomy, and some people like that, because it makes all the other problems of the world seem trivial. Okay. But I think another way of thinking about this is, we're these little creatures that are about 2 meters tall, that live at most 100 years. We live in a universe that's 14 billion years old, in a galaxy that's 100,000 light years across, 10 to the 21 meters across, so 10 to the 20 times bigger than we are. And yet we basically know this. So we've been able to figure all this stuff out. I mean, it's like looking down at an ant colony, but ants know everything. They know like where they live and what state they're in and what the zip code is. That's what we've done. So I don't think we should trivialize this, right? This is an impressive thing that humans have done. That I can tell you where we are. We live right here on this galaxy. It's called the Milky Way, and I know where all the other galaxies are. I know how long it's been there, etc., etc. And I can tell you how I know that. So I'm not going to keep going on with this forever, because this is kind of what the course is about. But I can zoom out another factor of 10. And that's where that Andromeda galaxy is that I've been talking about. This one that's 2.5 million light years away. That's where it is. So notice it's kind of different. Like, the distances between stars is really big. The basketball and the state of Hawaii. Distances. But this distance isn't so big, right? This is like a silver dollar and another silver dollar about 1 meter away. So galaxies actually like to live together, it turns out. They're not that far away from each other. And it turns out they run into each other all the time. But stars don't almost never run into each other, and they're very far away from each other on that scale. So there's another, about a factor of 10.5. And we can begin to make maps of the universe. So every single dot on this map is a galaxy. Okay? And it turns out that galaxies make grand patterns on very, very large scales, on millions and millions of light-year scales. They tend to orient themselves in groups, and also those groups tend to orient themselves in filaments. So long strings of galaxies that stretch out, that meet in knots, where there are bigger galaxies that build. Okay? And our galaxy is right in the middle of this diagram. It's hard to see. Keep in mind that every one of these dots has billions of stars, has about 100 billion stars in it. And if I keep zooming out, there's more and more galaxies. So this is even a bigger zoom out. Okay? Now, even the individual points of galaxies have kind of been smeared out. And what's done now is galaxies tend to live in these big groups and clusters of galaxies. Okay? We're living right in the center in a very small group of galaxies that we call the local group. The nearest big group or cluster to us is called the Virgo cluster. Okay? There is another cluster here that's called Coma. There's another one here that's called Sculptor. Does anyone notice anything interesting about the naming convention here? Coma, Sculptor. There's something called Hercules. Yeah, they're all Greek, but it's something related to that too. Something even more specific. Is anyone into horoscopes? Right? So these are constellations. They're named after constellations. Why are they named after constellations? Okay. The reason why they're named after constellations is, what are constellations, first of all, right? They're groups of stars that we see projected onto the sphere that we look out at. Okay? So there might be a group of, so there's stars that make up the Big Dipper, right? And it looks like the Big Dipper, to your eye, you think of the Big Dipper as being in this plane, right? There's the scooper and there's the handle, okay? But those stars actually aren't all lined up in a plane. They just look like that. Some are farther away than others. But when you see them on projection, your mind says, oh, they're all in one line. They're not. Okay? Anyway, when we look through the Big Dipper, there are galaxies that are behind the Big Dipper, right? There are stars in our own galaxy that we have to look past to see more distant galaxies. So the Andromeda galaxy lives in the area of the sky where the Andromeda constellation is. You have to look through the stars that make up the Andromeda constellation in our galaxy in order to see M31, which is outside of our galaxy. And it's the same thing here. Okay? So Sculptor, this large group of galaxies, large cluster of galaxies called Sculptor, just lives really far away, but in the direction of the Sculptor constellation, way beyond all the stars that make up the constellation. So that's the naming convention that's adopted here. But the naming convention sort of brings home the fact that we're looking through all of these stars that are sort of foreground, that are kind of in our way, so that we can see stuff that's far away. It's kind of like being in a forest and having to look past the trees to see the more interesting stuff that's outside the forest.